about Nur Izwani? Okay, that's from Nur Izwani. Najmi Aminuddin.
Hello, sir.
Yes, we hear you.
Uh,
It's okay, just talk. We try to catch it up.
uh, the ability for object to
Mm-hmm. Okay. We can hear you. I mean, the last one. Perhaps you speak it up, but we can hear you. You put to study. Najmi.
Hello, hello. Uh, kebolehan objek untuk bergerak dengan lancar dengan rintangan angin.
Okay. Right. The last one, maybe from Muhammad Izra. Are you here?
Yes, sir. Aerodynamic semua objek yang bergerak melalui yang berlanggangan udara satu
Okay. So everybody got the idea. Some of you told us that the waves berlanggar dengan udara. Okay. So meaning it's actually a flow past an immersed body, right? The car or the aircraft is actually the object, the body. So when you try to move forward within, okay. So yeah, so you know, air is actually one of the fluid as well. So it doesn't matter any kind of fluid. So any object that try to flow, try to move, okay, past a fluid. Okay. So meaning we have what we call as a flow past immersed bodies. Okay, so that's your answer. But basically, when we talk about aerodynamics, we always talk about the body itself, okay, the geometry of the body. For example, aircraft, right? We try to design the body to be what? As streamlined as possible, but they have lift or drag. Which one? Muhammad Nazri,
Yes, sir.
right?
Apa, sir?
Aircraft, we try to design for what actually? The body.
Tak jelas, sir.
Aircraft body, right?
Yeah.
For aircraft geometry. Okay. So we try to design the aircraft geometry to achieve what actually? What we want to achieve?
Daya apa kan?
Okay. Lift, right?
Yeah.
So lift cost. Okay. How about, okay, thank you, Nazmi. Right. How about car? We try to reduce what? Putri Dania?
Yes, sir. What's the question again?
Okay, just now is aircraft. So aircraft, we try to design the aircraft to be to achieve lift in order for aircraft to move, to fly, right? So how about car?
Car. Um. mm, uh, Drag force
Yeah, good. Is it to reduce or increase?
to reduce.
So you get the idea, right? Yes.
Thank you, sir.
So aircraft usually aerodynamics is not the flow. The one that you answer is correct, but as an engineer, what we know is when we talk about aerodynamics, we try to design something towards the body. Okay? So for aircraft, we try to achieve lift, but for car, like what Putri Daniel told us, we try to reduce the drag, right? So that's why an object pass through a fluid. So this chapter cannot run away with aerodynamics. Okay, this is the learning objective. Okay. So as you can see at number 4, calculate the lift and drag forces for various objects. So in the end, you can imagine in this chapter, the last one that they can ask is about drag forces and lift. So FL or FD, right? Okay. So from number 1, number 2, and number 3, I need to explain this one first. Okay. This. Okay. Every solid body have their own drag coefficient. Okay. So as you can see, sphere, half sphere, cube, streamline body, streamline half body. Okay, they have their own drag coefficient. If the body is bulky, right? Quite big. Okay. The drag coefficient, will increase. For example, here is cube, 1.05. But if the body is streamlined, it's actually 0.04. Okay, for example. Okay. Okay. And this one is actually combination of the drag is combination of two things. One is pressure drag, another one is friction drag. Right? Pressure drag is due to the so this is where I introduce to you, not introduce to you, we talk about frontal area. Okay, so this is the flow towards the body. So what the fluids see to the body is like this. Okay, let's assume this one is a cylinder. So from the front, they look something like this. So imagine if it is larger, right? So the drag should be higher. So this is pressure drag due to the shape. Another one is friction drag. Okay, so by the name itself, you should know that friction drag is due to surface of the body. So this is actually friction drag. So you've learned before that in chapter 1, when a fluid tries to move on top of a plate, there will be a velocity profile, right? Okay. So we have something like this. And your free stream velocity is this one, which is all 10 meter per second, for example, or 0.1 meter per second. But the thing is, when it is on top of a flat plate, it will look something like that, right? Okay, so this one is what? It's due to the surface friction. Okay. Okay, next I need this one to explain further. Okay. So let's take a look at the shape. So shape number 1, you have plate which is in vertical direction. So normal to the direction of flow. So yeah, you're gonna have drag, but all of them is because of the pressure drag. Friction drag is almost 0%. You can ignore the friction drag. Right? Okay, number 2. Shape number 2 is round. So now you can imagine, due to the roundness, okay, and the shape, so the pressure drag is less. Now it's 90%. But since we have a surface here, so you're gonna have about 10% of friction drag. This is not accurate value. This is just a representation on how the difference between shape. Okay, next is if you have streamlined body. Okay, so for a streamlined body, pressure drag is reduced further, become 10% because the frontal area is smaller. Like let's say this is continuous, it's actually smaller compared to this one is large, right? So pressure drag is reduced to 10%, but 90% friction drag. Okay, and the last one. Okay, even though that I draw the frontal area, but perhaps it looks something like this. So basically, it's really small compared to the first one. So it can be ignored. So that's why pressure drag is 0%, but we still have drag. But the drag is due to 100% of the due to the surface toughness or friction on the surface. Okay. So imagine just now what happened on top of the plate. You're gonna have the velocity profile look something like this, right? Okay. So it changed from the first one. I mean, the phrase in this chapter is this one. All about chapter 3 is about friction drag. Okay. So that's why if you see from your learning objective, boundary layer, okay, the boundary layer, velocity profile. So that's why from 1 until 3, calculate the boundary layer parameters for flow past a flat plate. Explain the physical process of boundary layer separation. So you never heard it before, now you know. Okay. Why we that why the learning objective is always about boundary layer. Okay. So our sample of study, since I already explained, 100% of friction drag can be achieved by a flat plate. So that's why our sample of study always a flat plate. Okay. So whatever happen on the flat plate, okay, either laminar flow, turbulent flow, transition flow, everything. The profile looks like. Okay. So we are not going to study about the shape, the frontal area, how to calculate the drag in terms of shape, right? No. Okay. But you've learned this one actually in Fluke 1. Okay, I want to ask. Afzatul Najwa,
Yes, sir.
Fluke 1, which chapter that you think relate to the drag? Can you remember?
Chapter masuk sir, chapter sebelum ni ke?
No, Fluke number 1. Fluke 1. Can you still remember Fluke 1?
Hmm,
Chapter 1 is what? Dimensional analysis, right? Okay, so that one is not related. Chapter 2,
saya tak pastilah sir.
I don't know. Okay. Maybe your chapters is quite thick compared to mine. But what do you think? Which tajuk yang berkaitan dengan pressure drag? Anyone want to help Afzal tu? Muhammad Irfan.
Yes, sir.
What do you think?
Related to friction drag, sir.
No, pressure drag.
Pressure drag. I think maybe pressure. If in fluid one, pressure fluid.
Chapter 3, pressure and fluid static.
Chapter? What is the title?
Pressure and fluid static.
Pressure in fluid static. Okay. So inside that chapter, do you guys still remember LME? What is LME? Linear momentum equation. Do you remember the one? Okay. Alright. So perhaps you need to refer back to the one. Okay. Because of what? Your assignment will, some of the assignment is not only come from this field 2, but a combination with knowledge from field 1. Okay, linear momentum equation. So basically, you're going to calculate the difference between two states. You have forces in terms of rho, v, and dA, normal to the velocity. So the mass flow rate, the momentum state 1 equals to momentum state 2. If you still remember, if I thought about this chapter, I'm going to teach on aircraft itself, the drag of an aircraft, as well as the lift. Yeah. So basically, it's quite clear actually. Okay. And also perhaps, you still remember this one? You have a elbow shape, elbow shape. So it's gonna be forced into this one and it goes out. And due to these forces, this elbow will move forward. Okay. So the one is actually a drag, right? Or pressure drag. So refer back to okay. So now what I'm saying here is chapter 3 is friction. Right. So pretty clear to you all. But we cannot run away with aerodynamics, right? Because it's part of aerodynamics. Okay. So I'm going to explain about chapter number 3. Okay. The brief explanation on chapter 3. So you're going to have this. Okay. If an object tries to move forward, we call that thrust. But when the fluid is menentang pergerakan itu, okay, so we call it as a drag. And then you're going to have a lift as well as the weight. Okay, let's talk about aerofoil. This is just a knowledge. Aerofoil. So just now is somebody told us that aircraft, right? So aerodynamics is when aircraft try to fly, the design of the aerodynamic is actually at the wing. So this is aerofoil. So what happens is you have a velocity separated bottom and top. This is bottom, this one is top. Okay. In order for you to get lift higher than the weight, if not, the aircraft cannot fly. So we try to design this one to ensure the velocity difference. Okay, velocity difference. Okay, what do you think? Which one is higher? This is V1. This is V2. So which one should be higher, V1 or V2? Nurul Huda. Senyum dia.
V2 sekarang V2.
Okay. Try to think of when you have higher velocity, pressure is reduced.
Oh,
That's the concept. So what do you think? In order for us to achieve lift.
V1 kena tinggi so that the pressure at V1 rendah.
Mm-hmm.
So V2 slow, pressure dia tinggi so dia akan naik. Is it correct?
Yeah. Very good. So that's the concept of it. Okay. So we design this red color aerofoil. This is just knowledge. It's not going to be in chapter 2. Maybe assignment, I don't know. Okay. So we try to design this one to achieve that. So V2 should be low velocity. V1 must be higher. So when velocity higher at the top, pressure is reduced due to that. And if V2 is lower, pressure is increased. So when you have difference of pressure, logically, this is higher pressure, P2, right? And P1, that thing downward. So since P2 is higher than P1, you can achieve lift. Okay. So if that lift is larger than the weight, the aircraft can fly. Right. Alright. Muhammad Nur Hafiz. Are you there?
Yes, sir.
Get me the weight, the curb weight of Boeing 747. Google for me now.
Boeing.
Get me the curb weight or the weight of 747, Boeing 747. Which one is larger, 747 or 777?
Hmm. Seven.
Okay, what is the curb weight? I mean the gross weight.
200 kg.
Huh?
200 kg.
Only 200 kg.
Wait.
Anyone want to help? Or anyone have found the weight?
Uh, 200,000 kg.
200,000 kg. So it's what? 200,000 meaning 200 ton, right? 200,000 kg. Am I right? 1,000 kg is 1 ton, right? Is it correct, Hafiz? So 200,000 kilogram. You imagine that, Hafiz. So is it the aircraft only, or when you have passenger? Okay, let's say that one is actually the aircraft, and then we add up passenger more into the aircraft, and then we add up your baggage, right? Hafiz, you dah pernah pergi terbang ke mana-mana?
Belum Ustaz.
Allah. Belum COVID tak sempat
Tak sempat.
after COVID. Okay. So in our payload, okay, thank you, Hafiz. So in our payload, maybe is what? It produced 250 ton. You imagine, right? With the design of the sayap tu that you told us just now, and the movement of aircraft, right? That's the concept, right? 250 ton of solid body can fly. Can you imagine that? Okay. So for you to not remember one, agak sedih lah. Because you want to become engineer, right? I believe some of you also want to become what? Maintenance engineer for aircraft. So when you learn chapter 3, okay, let's you need to imagine how important it is for you to learn this chapter 3. Okay. Even though you learn about one layer and all, right? But the thing is, the concept is you can produce an aircraft. 250 ton. And some more, you don't need what? You don't need any solid body to make it fly. Okay, the thing is, we just use what? Yeah, the sayap. But the thing is, it flows dalam fluid apa? Kapal terbang bergerak dalam apa? Minyak semua. Aircraft move in between what? Fluid region. Some of you mouthing the word. Okay. Adibah,
Yes, sir.
inside what? Aircraft move within fluid region.
Air region.
Adibah, can you feel air?
Yes.
Is it a solid?
No.
Ringan kan? Imagine ni kuasa Allah tu. Power. You breathe the air. Okay.
Just. The body
So you just breathe the air, and you know the air is only what? 1.2 kilogram per meter cube, the density. Compared to water is 1,000 kilogram per meter cube. So with 1.2 kilogram per meter cube, with the right design from human, okay. So even though the one designed by human, but the brain is come from, the brain of the human comes from Allah again. 250 ton of object can fly. So imagine that. Alright. we proceed. Okay, so that's why here you're gonna learn on the boundary layer theory, BLT on flat plate. Okay, so you're gonna have your free stream velocity at the front, and you have your velocity profile. Okay, the boundary layer. Okay, so we cannot ignore this one. Okay, I mean, new things for you, right? Before this, I introduced to you on chapter 2 psi, zeta. Okay. Now it's actually delta. Okay. So delta is actually boundary layer thickness. Okay. So we classify delta is actually the height from the flat plate to the 0.99 U string. Okay. So that is the height of delta. And next we have what we call as a displacement thickness. Okay, so displacement thickness is first I need to talk about boundary layer. This black color line is actually boundary layer. So let's say it's actually this delta 3, for example. This delta 3. So this is delta 2 at this position. And here is perhaps delta 1. So by um, connecting all this delta, so we're going to have boundary layer. Right. Next is if you see here, the boundary layer is growing. Okay? So when it grows, displacement thickness, okay, the name itself is actually displaced, right? Displaced. So imagine if you have a fluid that is actually increase, right? But the thing is, your object at the bottom is actually a flat plate. Okay, like imagine you are is actually in what? Dekat beach, in a beach, pantai kan? You see. So let's say um, there is a bump of water, and those bump of water perhaps due to a rock at the bottom of the lake. Jadi pantai lake lah, lake lah, for example, at the bottom of the lake. So there is a bump of water, and then after that tenang balik lah. Okay. Bump of water. So this one is you have a flat plate, but underneath this one you have a rock. So that's why you have a bump of water, right? So displacement thickness is actually an imaginary solid body. Imaginary, not there, because our solid body is only a flat plate. But due to this growing, we assume there is an imaginary solid body underneath. Like this concept, right? So it grows. So this height is delta star. Okay. So how you calculate? Use this one. From 0 to delta, 1 minus u divided by u string. Okay. Next, we talk about displacement thickness. Alright. So if this, momentum thickness. And the symbol by theta. So do not confuse, it's not theta angle, but this one is actually a thickness. Okay. For me to explain about momentum thickness, I'm going to use these two figures. I mean, these two velocity profile, which is the free stream velocity profile and this profile. Okay. momentum. Okay, imagine the total momentum is 10. Just assume no unit, only 10. Okay. So you have the arrow, right? All the same. The same width, so meaning free swim velocity, right? But the thing is, when it moves towards the flat plate, can you see the arrow? Some of them become lower. So meaning there is a loss of momentum from the free stream velocity. Now instead of this rectangle, okay, this one is rectangle. It becomes this one. So we have a loss here. The loss of momentum. So this one is delta. Momentum thickness. So how we calculate that one is using this. From 0 to delta, u divided by u stream, 1 minus u divided by u stream, dy. Any question? Muhammad?
Sir, momentum
Sorry, yeah. That's me.
momentum thickness ni loss of momentum ke? Dia punya region tu.
Loss of momentum.
Okay, sir.
Even if you see the equation, it's actually calculated by what?
It's 9 hours.
The area underneath the profile, this profile. Loss of momentum. Any question from you?
Keluar.
Okay. That's okay. Okay. That's me. Again.
Kurang jelas.
Kurang jelas. So,
Keluar.
okay, you want me to explain? Which one? Kalau ask me.
Saya rasa yang machinery ni.
Okay. At delta. Let's see, delta star. So you have this one. The growth of boundary layer.
Hello? Drag force.
Yes. Why that force? Why not lift?
Because no pressure.
Because of no pressure. No. What do you think? What do you think? Why not lift?
No idea, sir.
Okay, aerofoil, right? Aerofoil, if you take a look here, this one you saw. The design of aerofoil is actually a lot. Okay, we call that NACA. So normally, if you are involved with aerodynamics in aircraft, okay, when you design the wing and all, they have their own specification of NACA. Okay. So I put this center line. Center line is should be straight line lah. Okay. Top and bottom cannot be the same. If it is the same, velocity at the top and velocity at the bottom is going to be the same. So nothing happen, right? So top and bottom is not going to be the same. So that's why we're going to design it differently in order for us to achieve lift. Okay, one Yusuf. But why we can only determine drag only for flat plate?
Because it's just flat.
Yeah, very good answer. Correct. Because it's only plate. Okay, drag due to friction. Clear, one Yusuf?
Yes, sir. Clear, sir.
Nak jadi aircraft engineer tak? Okay. So in order for us to calculate drag force, is actually equals to tau shear stress VDX. Okay. So now we go to the tau. This is our final objective. So in order for us to determine tau, we need this one. And this one. Okay. So in order for us to determine this tau, we need this. So apa ni? Momentum. Right. So after determining momentum thickness, then we can determine tau. Then we can determine drag force. Okay. So that's how actually in this chapter. Okay. So yeah. So in order for us to determine theta, which is momentum thickness, take a look at the equation. In fact, all of them, what? Ada 1 minus u divided by u stream. So, right? U divided by u stream. So, u divided by u stream is the representation of the equation of velocity profile. Okay. Now we go to the velocity profile equation. Okay. So, this profile, yeah, the one that I draw it here is it looks like this, but the thing is not always gonna be like this, like this, like this. Okay. So it can become linear, and it can become what? Sinusoidal. It can become parabolic. Okay. So in order for us to determine u divided by u stream for linear, we're gonna use this equation. Similarly for sinusoidal, this equation. And so on. Parabolic and cubic. Okay. Right. But before that, I almost skipped about laminar and turbulent flow. Okay. Okay, first is laminar and turbulent. Okay, if you want to increase further your boundary layer, perhaps it's gonna look something. So that is your boundary layer. Sorry. not going to be like that. It's going to be still like this, growing. But the thing is, here is lamina. So here is the flow is become transition. And this one is the flow underneath the boundary layer become turbulent. Okay. So for lamina and turbulent cases, as well as transition, this is lamina. This is transition. And this one is turbulent. They have their own equation. Okay. So how to calculate that one is you're going to use Reynolds number. Okay, somebody give me the equation of Reynolds number. So from fluid 1. Natasha.
Yes, sir.
Equation of Reynolds number. RE equals to rho it's okay, Natasha, Google. You can Google if you want to.
RE equals to rho UL over mu.
Yeah, right. Okay. Thank you. So Reynolds number is rho UL over mu. Okay. Okay, but the thing is for our case, you're gonna use X. So at any location, let's say X1, and this one is X2, right? Okay. So instead of rho UL, okay, we're gonna use rho UX. Right? Okay. So you're gonna calculate this one. Okay. So if the value is less than, oh, can you refer to the notes? Ada tu dalam tu. Okay. If the value less than some value, 1 times 10 to the power of 5 volt. Okay. So take a look at the notes. So if less than that value, Reynolds number, meaning your flow is laminar. If more than some value, again, take a look at the note. Saya nak cari next time. Okay. You're going to produce turbulent flow. Okay. So first what you need to do, determine Reynolds number and determine what kind of flow that you have. And you need to apply a different set of method or equation. Okay. So now I'm talking about the equation itself. So we have approximate approach and Blasius approach. These two are for laminar flow. Okay. So as you can see here, approach A, meaning this one. This is approach A. So you're gonna do linear, sinusoidal, parabolic, and cubic. Okay. So you're gonna what? Derive all of it. You put it into the delta star theta and then get all the tau based on this approximate approach. Second method is Blasius. Okay, so what is Blasius instead of derivation? Okay, you don't need to derive, or you don't need to produce some sort of integration and all, or differentiation. Okay, Blasius solution is directly given, which is this one. Okay. For example, delta is delta star. For approximate approach, you need to put it into this equation. If your problem is linear, for example, so you're going to put y over delta into this one. You need to integrate and all and get the final answer. But for Blasius solution, directly given. So this is the value of Blasius solution. Delta is 4.91x divided by square root of REX. What is REX? Just now, right? So UX divided by mu. Delta star, theta, CD. So that is approach B, which is Blasius solution. Lamina. Okay, next is turbulent flow. Okay, so for turbulent flow, we're gonna use approximate approach. Okay. It's not Blasius solution, but we have some form of direct equation. But normally what we do is we're gonna derive for turbulent flow. Okay, so the equation will be this: u divided by u stream equals to y over delta to the power of n. Okay, so this n can be anything. Can be 1 over 5, 1 over 7. Can be anything because the balloon flow is chaotic, right? We don't have any form of turbulence. It can be any kind of fluid flow. So that's why the power of any value. For lamina is obvious, only a straight line. So we can basically determine that. Okay. So that is all for about chapter 3. Okay. The whole summary on chapter number 3. Any question? From any of our friends?
Sir?
Who's that?
Naufal.
Naufal.
Sir, equation turbulent flow U over US equals to Y over delta over power N itu untuk linear turbulent flow saja ke apa? Ke untuk turbulent flow velocity profile sekali?
Okay. Like I mentioned just now, turbulent is what, Naufal? What is the characteristic of turbulent flow?
Aku sih tak dengar.
What is the characteristic of turbulent flow?
Hari ini banyak characteristic.
How it looks like? Sorry, how it looks like?
Turbulent, circular flow.
How turbulent flow looks like?
Macam dia punya trail circular flow.
The flow is everywhere, right, Naufal?
Oh yeah, okay.
Okay, so basically we cannot classify it into linear, into parabolic.
Oh, okay. Faham.
Okay. So yeah, it's too chaotic. Even let's say later you're gonna go for computational fluid dynamics, which is part 7. Part 7, you're gonna choose your subject, right? What we call that? Elementary subject.
Elective, sir.
Sorry. Thank you, Adima. Elective subject. Okay, you can choose, right? So one of them is computational fluid, dynamics. Okay. So in that subject, when we try to derive turbulent flow, basically not there's not one form of equation. There is, but the thing is, it must be based on application. Okay. So perhaps in automotive industry, how basically we assume the flows is based on this equation. So let's say this equation only valid for automotive industry only. Because of what? Um, yeah, the car movement is only highest velocity is perhaps berapa? Kereta you all biasa you bawa Adibah, you bawa kereta berapa laju?
80.
Paling laju 80 je Adibah.
Saya tak lesen.
Saya tadi baru 80 km sejam pergi kerja. Dah ada orang high beam sebab saya buat 80 je. Okay. So the thing is, not 8. Paling laju pun maybe 180 kot. Okay. Standard. Maybe somebody can get 240 km per hour. Okay. 180 km per hour. So, the turbulent flow causes by the car movement, only that kind of characteristic. But if you want to use the equation just now for car to what? To predict the turbulent flow for aircraft, which is moved at 560 km per hour. So it's not correct. So there's no one form of equation that valid for all. Okay, so for that's why for this case, back what Naufal asked just now, good question. Okay. There's no linear, there's no parabolic. So only that u divided by u stream, y over delta. Okay, we have terms of delta there and y, and we just put the power of something, 1/5, 1/7. But those 1/5, 1/7 is of course already represent observation of turbulent flow, right? Kita bukanlah main letak saja. We are not mathematician. We are not mathematician. We are engineer. When you is actually as an engineer, you are bound by logic. Mathematician, no, it doesn't bound by logic. So meaning y over delta can be 25 divided by 67. The only thing is you can calculate. But 25 over 67 is not, for example, it's not available in real world. That is the difference between mathematician and engineer. Okay. Like I mentioned before, okay, we discussed on 3 dimension, right? 3 plus 1. But for mathematician, they can calculate up until any dimension. 40 dimension, 50 dimension. But is it there? Tak ada kan? So that is mathematician. Alright, any question? Okay, so if no, since bulan puasa ni, dah rehat kot. Bila saya explain tadi buat mathematician, bola-bola sikit, you dah rehat. So just proceed next to next chapter. Okay, so we're gonna use this one, parabolic. Okay, so now is the time for us. Sorry, is it parabolic? Yeah, parabolic. Now is the time for us to try to derive this equation. Okay. Okay, parabolic profile. Okay, so this is parabolic. Alright, so bear with me. Okay, I'm gonna try to derive it one by one until the end, until the fast. But the idea would be when I introduce to you about parabolic, I derive for you parabolic. The same concept, you're gonna apply it for linear, sinusoidal, as well as cubic. Okay. So we're gonna start with, as you know, parabolic is this one. U divided by U stream equals to what? 2y over delta. And then you're gonna have what? Negative y over delta square, right? So before we go there, we put the u divided by u stream into delta star and theta. Okay. First, I'm gonna derive for you the parabolic profile itself. Okay. So we're gonna start with this one. U divided by u stream equals to b naught plus b1y plus b2 y squared. Okay. So the maximum power is actually to power of 2. So what we want is actually, in order for us to determine this one, we need to find this value. B0, B1, and B2. Okay. So what we're gonna do next is we try to rearrange our equation to look something like this. So you're gonna have u equals to u stream and multiply with b naught plus b1y plus b2y squared. Okay. So next what we do is we're gonna differentiate. Okay. Differentiate u towards y. So meaning all this term is differentiate. We need to differentiate towards y. Okay, do it now. So it becomes what? U stream multiply with Anyone?
B1
B1
plus
plus
2B2Y.
yes, thank you. Right, 2B2 Y. Alright. Next is differentiate it again. Okay, so continue. So, anyone have answer for this? Use stream, yes.
2B2.
2B2, very good. Okay, use stream. Okay, so this one looks familiar, right? So we have our u, du over dy, del square u over del y squared. Remember back chapter 1, so what we need to apply in order for us to determine B0, B2, and B1? We need to apply what? Muhammad Nazri Muhammad Anwi.
Yes, sir.
So after we done that, what do you think we need to apply? Like what we did in chapter 1.
Not sure, sir.
Refer back chapter 1, you can refer based on the one that we discussed before. Okay, Nurul Huda, what do you think? Muhammad Nazri.
Infinity equation ke? Oh,
What is your answer? Sorry?
Infinity equation.
No.
Bukan.
Remember back chapter 1.
Heavy equation.
Come again, Navier-Stokes.
Navier-Stokes equation.
No.
Oh, bukan juga.
That one is cancelled out. But the thing is, we apply something in order for us to get the constants. Boundary.
Boundary condition.
Boundary condition. Okay. So we need to apply BC. Boundary condition. Okay, so now take a look at boundary conditions. Okay, so boundary condition is valid for all, not only for parabolic, but for all linear, sinusoidal, cubic. Okay, boundary condition. Okay, so here, this point, we call this as leading edge. So leading edge is where the axis is positioned. So this is x direction. And this one is y direction. So at leading edge, what is the position for x and y? It's going to be 0x and
0Y.
0y. Origin, right? Origin of the axis. Okay, now take a look at our profile. Okay. Our profile will assume to be something like this. Even though it is parabolic, cubic, or sinusoidal, but the thing is, when we apply boundary conditions, we assume it to be like this. Okay. So you're gonna have BC, and you're gonna have BC, which is this height is just now is what? What is this height?
Momentum loss.
Again?
Momentum loss.
No. Atas sikit. The one at the top.
Boundary layer thickness.
Yes, delta. Okay, this is delta. Wow, Allah Akbar. So suppose okay, you need to imagine on top of this delta, the marker, sorry. On top of this delta, beyond, okay, beyond is actually U stream, meaning the velocity is the same. Okay. Give me this one, somebody. Boundary condition 1. At y equals to malu-malu you all ni. Putri Dania at BC1 at y equals to we can't hear you.
At y equals to 0 ke?
Okay.
At y equals to 0.
Okay. You
U U equals to the answer. Saya akan cari. U equals to
you can in fact refer to the chapter 1. On top of the plate.
at U equals to V ke?
Take a look back at my position.
At y equals to 0.
U equals to
U equals to U max ke?
okay. The idea is the larger the arrow, the bigger the velocity. So what is the arrow this one at this position?
Small arrow.
So meaning
U equals to 0.
yes. So U equals to 0. Right, so we just take a look at the arrow magnitude. Even though this is only sketching, but it actually represents something. Clear? Then Putri Dania, are you clear?
Yes. BC2 at y equals y equals to h. At y equals to h.
Okay.
U equals to u max.
Yes. Almost correct, but we're gonna yes, correct. But the thing is, we're gonna use a different kind of representation of U max. So what is U max here?
Delta.
Yeah. So Y now become delta, right?
Hmm.
So Y equals to delta, and then U equals to
U equals to delta max ke?
we always talk about U is U, not U is delta.
Okay. U equals to u max.
Yes, U equals to
U max.
Thank you. Very good.
Sorry, sir. Thank you.
So yeah, instead of H, but the thing is our H here is actually delta, right? So now it's actually U equals to U maximum. But the thing is, since we know our representation of U maximum is actually U stream. So instead of U maximum, we're going to use U stream. But of course, it's actually the maximum value of velocity. Okay, so we have 2 BC now. So we're gonna have another one actually. It is also representation of BC2, but I'm not gonna use BC2A or BC2B, even though same. But I'm gonna use BC3. Okay. So for BC3, the same in this position as well. At Y equals to delta, what can replace U maximum? Chapter 1.
V.
No. The change of something towards something does not change. Okay, du dy
Equal to 0.
very good lah. Okay, so du over dy equals to 0. Okay. It meant the same. Okay. But how we represent it is actually different. Okay, it comes from what Dania explained just now lah. U equals to U maximum. But the thing is, we're not gonna use U maximum because our equation always using US, right? U stream. So instead of that, we're gonna use U stream. So another representation of U maximum, du over dy equals to U. Okay, so another one, BC number 4. Okay, so for BC number 4, I'm gonna apply it on the here on top of the plate. Okay, at y equals to 0. Okay, now we talk about shear. Okay, we talk about shear. Okay, so from Navier-Stokes equation, shear is actually the mu, right? Mu equals to take a look back your Navier-Stokes equation. You have del squared u over del x squared plus del squared u over del y squared and then plus del squared u over del z squared. So perhaps this is the last one. We're gonna end up with this one. I mean, I'll leave with boundary conditions and ask you to find B not B1 and B2. Okay, I'm gonna explain this one. Okay, remember, this one is changed with what? U changes with what? Who else? Nazrin Shah. Yes. So the U changes with what actually?
Delta.
Okay. Remember back our velocity profile in chapter 1, the arrow is actually represent the magnitude of velocity. So meaning we have 0, and then we have 2, and then we have 4, and so on. So this one is changes of velocity. 0, 2, 4, changes with what direction?
Y.
Yes. Clear, Nazrin?
Clear, sir.
So meaning, we ignore this one, right? It does not relate at all with our problem. Okay. So what we need to concern is this. So in this position, kosong kan? Nothing's there. So meaning, this is our equation. Del squared u over del y squared is actually 0. So that is BC number 4. Any question? This is quite important because all linear, parabolic, sinusoidal all use the same boundary conditions. Any question at all? Muhammad Irfan Haifi, is it clear?
Clear, sir.
Anything you want to ask?
No, sir.
Okay. So you represent all your class member, right? So hopefully you all understand. Okay. Alright, so that's all for today. Okay. So we're gonna wrap up with this one, the boundary conditions. But by using this boundary condition, please find B0, B1, and B2. Okay, try. Find it on your own. In order for you to know that your answer is correct or not, later when you're gonna put back in this equation, B0, B1, B2, you're gonna get this one. Okay, so try it at your own free time after you dah maybe after sahur ke. Okay, up to you. Menunggu buka ke. Right. Right. So I think that's all for today. So I'm gonna give you your attendance. Any question you can still ask. I'm setting up your attendance. Just want to ask, you all ada cuti mid semester, correct? You know your own jadual? When is your mid semester date? Yes, Anis. What is the date?
Kejap saya check.
Start 8 Mei.
8. 8 Mei.
8 Mei, eh? Alright. So 8 Mei until
Sampai 16 Mei Ahad.
8 Mei sampai
16.
16 Mei Ahad. Okay, 8 sampai.
8 tu Sabtu.
So today is what? 22nd.
22nd.
Huh? It's March. Today is 22nd. So 8 Mei is your cuti. Right? So meaning next week we still can continue with chapter 3. But during the following week, which is 3 until 7, okay, we're gonna do tutorial for chapter 1 and chapter 2. Okay? Because after Raya tu, probably or perhaps is your ODL exam 1. Okay. Okay, fill up your attendance. Thank you, Anis and somebody tadi. Okay, for your ODL exam 1, yeah, even though you need to switch on your camera. So everybody need to switch on their camera. So that's it. That's the requirement for my ODL exam 1. So like this, or more like this. So I can see how to answer your question. So make sure your try to set up your camera. If your camera has a problem, meaning your laptop camera has a problem, use your phone camera pun boleh. Meaning letaklah kat tepi tu. That's all. Okay, 25 students. Alright. So I think that's all for today. So we end our class with Tasbih Kifarah and Surah Alright. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam. Thank you, sir.
Thank you, sir.
Thank you, sir.
Waalaikumsalam. Thank you, sir.
Thank you, sir.
Okay, sir.
Alright, thank you. See you all.
Assalamualaikum.